Morning from Bern. He's going to speak about a tensor restriction theorem over finite fields.
Okay, thank you. It's a pleasure to be here. Well, I would like to discuss the mathematical aspect of partial order on tensors. Partial order, we all know, is called restriction. And in fact, as you will see, it's a kind of restricted form of restriction. The theorem that I want to discuss is a kind of coarse structure theory for restriction-closed tensors. So here we go. The setting is the following. You fix a field, which I denote K, and it is a finite field. And will be convenient to have a notation for the category of finite-dimensional vector spaces over K. And now I'll fix the integer. And then if you have two tensors, S in, say, V to the tensor D, and T in W to the tensor D, where V and W are objects in vector. Then we say that S is less than or equal to T if there exists a linear map phi from W into V such that phi to the tensor D applied to T is equal to S. So this is called S is a restriction of T, because you can think of T as a multilinear form of W star to the power T, and then, well, at least if phi is surjective, then you can think of the dual of phi as an injection from P star to W star, and then you can think of S as a restriction of that multilinear form to the image of V star to the power T. This is W star to. And so the theorem, which we recently proved with Andreas Blatter, who is a student in Bern, and Rupniewski, who is a postdoc in Bern, former student of Zariski-closed, and myself, says that if you are given tensors Pi in Vi to the tensor power V, so V is fixed here, and K is fixed. What is not fixed are these vector spaces in the tensors. I runs to 1, 2, 3, and so on. Then there exists an I less than J, but that Pi is a restriction. That's what I would like to call the or a tensor restriction. Right. So this says that restriction for tensors is what is often called a well-quasi-ordered in combinatorics, in computer science. Maybe in math it's called like something like a well-pre-ordered or something. Anyway, this is what it is. So maybe the first remark is that.
Can you say it again? So for every countable collection of tensors,
there is one
comparable pair. Yeah.
So there are no infinite transactions.
Yeah.
I'm a little puzzled because the phi is also tensor N, tensor D. So it's the same that you apply on all of them.
Just symmetric restriction.
That's my first remark. So often in computer science, we look at a slightly weaker or stronger, depending how you want to call it, notion of restriction, which is that you allow D different linear maps here, and maybe also D different vector spaces and D different vector spaces here. In that setting, the theorem is also true, but it's actually weaker than it is like this, because here we require that you take the same linear map in all of the D vectors. So this implies the result.
There's a T sum
result where you allow.
Yeah.
Let's say 1 tensor phi t.
But there's no restrictions on the S's and T's, so they don't have to be symmetric in any way.
They don't have to be symmetric, but of course they may be, and then you also get the theorem for
Sure,
symmetric.
understood.
Yeah.
It implies it for the non-symmetric for different phi's.
It implies it because this is because here you are allowed to you have more of these inequalities, and this says there's a strict rating.
Yeah,
that's the first remark. The second remark is that is it not true when the field is infinite?
Very showing.
But I'll say something that is true when the field is infinite. And in fact, suppose that you just take D equal to 2, and you take MA equal to the matrix 1, 1, A minus A, fitting in K2 tensor K2, where A runs through the field K.
That makes sense.
But since here if you would allow such maps, then these would be all comparable. But since we are allowing only one map like this, then these are already not comparable, or mostly not comparable, because MA is less than or equal to MB. What would that mean? Well, that means that there exists a phi, say a 2 by 2 matrix of the field K, such that phi and B phi transpose is equal to MA. And this is how linear maps act on tensors. And this would imply that phi is invertible because the rank of those two matrices are the same. And then if you look at the symmetric part of these tensors, that is just the identity matrix. So phi has to be orthogonal, right? Because it must map the symmetric part of this tensor MB to the symmetric part of the tensor MA. And hence MA is conjugate to B MB. So that means that in particular, what do I want to say? Well, in particular, the determinant must be equal. So in particular, 1 plus A square is equal to 1 plus B square. And so A square and B square are equal to each other. And if there are infinitely many elements in the fields, then you find some infinite anti-chains. It is infinite and bar infinite anti-chains. Secretly, I use here that the field has characteristic not 2, otherwise you cannot talk about the symmetric part and the skew symmetric part as I did. Also, when the field has characteristic 2, but it's infinite, you can find.
Does that argument also go true if you allow phi 1 and phi 2 to be different?
No, in this case, of course not. So for matrices, this statement is kind of trivially true if you allow phi 1 and phi 2 to be different because they are characterized by rank. But already for 3 tensors, again, it's not true when the field is infinite, and if you allow a different path.
Okay.
So what size?
I don't know. I did it.
It's easy to get this with
Probably count dimensions. So I think of this theorem as a kind of multilinear analog of the graph-minor theorem, which says that if you have an infinite sequence of infinite sequence of graphs, then there are 2 that are comparable to each other, where one is a minor of the other. I don't know of any logical connection between the 2. But the graph-minor theorem did serve as kind of inspiration for this theorem and also for the corollaries that I'd like to describe. So In the case of graph minor theorem, you study properties of graphs that are preserved under taking minor. So you study properties of tensors that are preserved under taking restrictions. So let's say a restriction closed tensor property. Well, what is that? Well, it's just the data of a subset X of V sitting inside V to the tensor D. This D is fixed in this story, such that for all phi V to W linear maps, we have that would be tensor power of phi maps X of V into X of W. That's what's a restriction closed tensor property. And some examples. There's various notions of rank that are restriction monotone and hence being of rank most something is a restriction closed tensor property. So for instance, you can do this for say slice rank. At most some given number, or partition rank, or which other ones? You can think about asymptotic subrank, or just asymptotic rank. Yeah, all of these are properties that are preserved under applying linear maps. Then there are different types of properties, like the ones that Matthias referred to, like being symmetric or maybe skew symmetric. And there's a lot of stuff in between, coming from various Young diagrams on with D boxes. If your tensor is symmetric in V to the tensor D, then it remains symmetric when I apply the tensor power of a linear map. And then there is kind of other funny properties like X, let me say, not greater than T. It may be called T0. So what this means is that you look at all the T in V to the tensor D, such that T0 is not a restriction of T. Right? If you have two tensors, if you have a tensor that does not restrict to T0, and you take a restriction of that tensor T, then it still doesn't restrict to T0. So this is kind of some examples of restriction closed tensors. And so then the corollary.
Yeah. Sorry, so from the examples, I think I know what you mean with a restriction closed tensor property, but I'm not quite sure how to read the data of X of V.
So for every subset, for every vector space,
yeah,
you have a subset X of V sitting in V to the tensor D,
such
that if you take a linear map from V to W, the tensor power of that linear maps to V.
So what's the data?
So actually,
Well, okay, so sorry, you know, I don't. You can, so a tensor property, so to give you a tensor property, I have to give you some data, and this data is for every vector space V, a subset of V to the tensor V.
it's like either you give the function slice rank or you give the set X of V.
Okay.
They encode the same data. I think that's like X of V would be all tensors in V to the D of slice rank at most.
What we watch about is then it is a sub-functor of the functor that's in V to the V to the tensor D, but you have to think of this functor as a functor to sets and not to vector spaces. And then it is that's what restriction is. But I don't think it's more useful. But maybe, and I understand that you're feeling uncomfortable about this, but as a consequence of this theorem, every such tensor property has a finite description. So maybe you like that. So the corollary the corollaries are like this. So let me start with that one. So every
You need to satisfy something.
restriction closed tensor property
Six of these.
It's to be close.
Huh?
Yeah, the closeness.
Close. Under 5.
property X is of the form X is not bigger than T1 and not bigger than Tk for some tensors T1 up to Tk. It's like every minor closed property of finite graphs can be described by finitely many forbidden minors. In the same way, every restriction closed tensor property can be described by finitely many forbidden restrictions. Second is the second is actually the one that we usually prove. Namely, if you have a sequence of restriction closed properties, this symbol here means that for every v, x1 of v is a subset of x2 of v, then there exists an m such that from that point on all of them are equal.
So this is a corollary of the truth.
Yeah, these are the easy corollaries of the theorem here. And in fact, everything I'm writing down so far is easily seen to be equivalent to the theorem as I wrote it at the beginning. I just like the formulation in the beginning because it refers to actual tensors rather than quantifying over subsets of over restriction closed tensor. You see, the third one is did I want to say? Yeah. So every restriction monotone function on tensors, let me say R values function on tensors as a well-ordered set of values. And on tensors so everything that I said at the beginning is fixed, namely the fixed finite field and the t, the size of the tensor is fixed. And by restriction monotone function, I just mean that it can only become smaller if you pass to a restriction. And then the last one is for every restriction closed tensor property X, there exists an M0 such that you can test the property X by looking at principal subtensors of this format. Or such that let me say it like this. For all n greater than or equal to M0, the tensor T in k to the n to the tensor D has property X, if and only if all the subtensors of this format have it. So all principal subtensors of D of size and 0 times 0 at property X. So this is very closely related to Thomas Karam's talk this afternoon, which discussed it, tensor properties like being slice rank or partition rank or more complicated notions of tensors.
For the well-ordered thing, what does it mean? So we take the standard order on R.
Yeah.
And
yeah.
So it means every subset has a smallest element, right? That's
every subset has the smallest element
of that set of values.
Of that set of values. That's right. So actually, there's a paper that I think is not yet out by Fulvio. Are you involved, Matthias?
Yeah.
So in the case of asymptotic subrank of tensors I guess maybe of the complex numbers you should.
Yeah, or
you know,
arbitrary closed.
You show that the asymptotic subrank is either one or bounded away from one. And you found the next value.
Mhm.
And so this theorem said, at least over a finite cube, there is always such a next value. So also maybe, you know, for three-way tensors, if you look at asymptotic rank, after 4 there is a next value. So either matrix multiplication has asymptotic rank at most 4, or it has at least 4 plus epsilon, where this is true for all tensors, all 3 tensors.
Yeah.
I mean, there's no values in it. Okay, let me now say something also about infinite fields. We already saw that, as stated, the theorem is not true for infinite fields, but some versions of it are. So, namely, which ones? I guess 2 and 3 and 4, they have analogues over infinite fields. However, they are not good enough to, for instance, prove that here, well, to give this result for asymptotic subrank. Provided that the restriction closed central properties are Zariski-closed. Yeah, so every x of v should be a Zariski-closed tensor property, a Zariski-closed subset of v to the tensor t. There's no mention of a restriction closed property in 3, but there the function should be semi-continuous, respectively. The function, I always forget what this is called, lower or upper semi-continuous, so let me just say semi-continuous. And what I mean is that, so if this is the function, it can drop in the limit, but it cannot go up in the limit. Like matrix rank. And so interestingly, over infinite fields, this is already much older. So this follows from work that I did a few years ago. And it's also quite a lot easier than in the case of finite fields.
So what are good examples? Because
Sorry,
what are good examples of such functions?
Such function, that is a good question.
Like for which the well-orderedness is like non-trivial also, because
So
the slice rank takes integer values, for example. So then
of course there it's kind of boring, but you could look at the Zariski closure of the set of all tensors of asymptotic. I mean, you could kind of artificially make it like this, right? Yeah. But then you're right that we don't really know. So it would actually be very interesting, I think, to understand over infinite fields these kind of things which have I don't really know what to say. It would be interesting to understand more general restriction monotone functions. So maybe an example of this item 3 is this notion of analytic rank, which I think will feature in Alex afterwards. So, for example, if you think of a tensor as a multilinear function into the field, then the analytic rank of T is minus the logarithm of the expected value of say x1 and 2 xn, we start with the tensor d, and then take chi of t of x1 up to xe, where chi is an additive character, and additive, and I guess non-trivial character. Yeah, a priori, it's a little bit surprising that this is actually a positive real number, but it's also descriptions that do not use this character. But this would be such a restriction monotone function. So by this item, I guess maybe it's called 3. This takes a well-ordered set of examples. I must admit, I have no idea what that set looks like. Maybe this is quite an easy statement. I don't understand this analytic rank well enough yet, but
because the values of analytic rank are not necessarily integer, right?
yeah, no.
So
That's
so a priori you could get like it could converge, like you could have like dense. Yeah.
This is
Also because like it's constant on orbits, but of course it can be infinite many orbits, etc. So yeah.
That's what I mean now at second point.
It just means it's gapped.
yeah. So maybe I should mention. So Alex will speak about this relation between analytic rank and partition rank. From the proof of this theorem, you can easily get some statement like each of them is bounded in terms of the other, but you cannot get nice statements. You cannot get good bounds of the proof of this thing. Okay, so I wanted to say a little bit about what kind of things go into the proof of this theorem.
So wait, so the connection between partition rank and analytic rank does not imply this well-orderedness statement?
Oh, maybe it does.
Because partition rank is always integer.
Maybe it does also.
I don't know. That's of course not such an easy.
No, it's just a bound.
Yeah, it's just a bound. So
It's just a bound.
I don't know. Maybe it's not strong enough.
So the first proof, the first aspect of the proof is that, well, I said everything for tensors, but I mentioned symmetric tensors and skewed symmetric tensors and so on. And actually, to prove this theorem in generality, you have to prove it for a bigger class of vector spaces that vary functorially with the vector space. And so the theorems, so the theorem and the corollary are true for arbitrary functors. V from vector to vector. Yeah, so this just says that to every vector space you associate a vector space, and to every linear map between vector spaces you associate a linear map between the corresponding vector spaces V. Like phi goes to phi to the tensor V. This is not quite true. This is a too large class, but it's almost true. Namely, there's different ways of saying this, but for instance, what I can say is such that the dimension of P of k to the n is a polynomial in n. Yeah, like for instance, if you look at P to the tensor D, that has, when you evaluate it at k to the n, you get k to the n to the tensor D, which is n to the d dimensional, so that's a polynomial in n. Whenever you have any functor from here to here such that this holds, then the theorem is true. This looks like a more general statement. I guess it is, but it's not much more general because these functors, they form an abelian category. You can take direct sums, you can take quotients, you can take kernels. And in that abelian category, every such functor actually is a subquotient of a direct sum of finitely many things of the form V to the tensor sum. Yeah, so the greater generality is just in this, well, you're allowed to take direct sums instead of just one tensor like we were doing before, and you're allowed to take some sub-quotients. Something like symmetric, and then maybe symmetric tensors are not irreducible over the fields K, and then you can quotient out something, some irreducible part in there. So it's not a much more general statement, but actually in the proof you need its generality because we do induction over this functor P. Induction over P. So well.
So P could be like taking V to the power D. Is that what you're saying earlier? Like what's the role of what's P here, for example? Like
here is V goes to V to the tensor D. Yeah. But you could also think of symmetric powers or alternating powers.
Mm-hmm.
Yeah.
Slater rank for fermionic or antisymmetric tensors would also be fine.
I don't know what is that.
So the number of so if I define
like
so you know I take like V1 wedge V2. So I work in an antisymmetric power, and I take V1 wedge V2 wedge V3 and so on, and I call that a simple tensor. That's typically called a Slater determinant. Or
then yes.
And then I ask how many of those do I need to represent a thing. I call this the Slater rank, say. Would that also be covering that?
Yes. Okay. It's a secant varieties of the Grassmann.
Yes.
Yeah, that's also it's a special case. I guess in this case it's also already a special case of the original theorem because
just alternating, you know, I redefined the what. I mean,
no, that's the only difficulty is whether wedge D sits inside V to the tensor D, which depends on the field, on the cardinality of the field, whether it's smaller than D or bigger. But if the characteristic of the field is bigger than D, then it is a special case of the theorem as a statement. Okay, so I'm happy to once say a little bit more about this induction, but maybe not right now. So the other proof ingredient is that we think of these, even though we are in a completely combinatorial setting, we think of these tensor properties as varieties, as given equations. So we think of x of v sitting inside p of v. Then now you can think of this as v to the tensor d, or as wedge d of v, or some other functor like this, as variety given by equations in just to, because it helps us to think about things because it gets us inspired from, say, classical algebraic geometry. We write this like this, k of pv, but this is just a set of functions from p to k. Yeah, we're working over a finite field, so every function from here to here can be described as a polynomial. And in fact, there's a polynomial where all the exponents are strictly smaller than the cardinality of k. And we exploit that fact that such functions can actually be regarded as these kind of restricted polynomials. Just like every function from here to here can be described as a polynomial, every subset of PV can be described by a polynomial equation. We use that, and then we do a kind of induction over the degree of these polynomials. So it's a kind of nested induction. It's an outer induction that takes care of this P, and an inner induction that works with the degree of these polynomials. Okay, let me maybe say one more word about what I mean by this vanishing idea of X. So so we have these functors. V goes to PV, which is a covariant functor. I should have said that, but I'm saying it now. And then we have a functor v goes to the dual v star, which is a contravariant functor. And then we have functor. So this is the dual space. We have a functor PV goes to k of v goes to k of PV. This is also a contravariant functor. And you can think of this as the symmetric algebra on PV star, modding out things of the form x to the power q minus x, where q is the characteristic, the number of elements of the field. And so where does this ideal of x live? Well, it lives in this guy over here. Say I of x sends v to the ideal of f in k v such that f restricted to x v is equal to 0. And that's an so you should think of this. This is an ideal in k of p. Yeah, so part of the game here is that you start abstracting from this v. So you just so this is really a functor from vector spaces to algebras, and that is a functor that sends a vector space to an ideal in the corresponding algebra.
Jan,
Yeah.
this the polynomial equations you need, like the number of them or the degree of them, does it have an effect on the n that you had? I think you erased.
Oh, the n0
In part 4 of your corollary, you have n0,
Yeah.
which is a bit. So
Yeah.
is that does the way in which you describe xv in terms of polynomial equations translate back into a bound on this end?
In certain cases, it does. The degree. So in the case of so in the case of partition rank, well, okay, there's not a direct relation, but in the case of partition rank, we can get some bounds by knowing some degrees of polynomials.
Yeah, so these degrees are of importance.
Yes, the degrees are actually quite important.
But the number.
And now that you mention it, let me explain also the thing that is missing for this item 4. First, finish your sentence.
So the number of equations, is that important as well?
Yes. If you want to know it precisely, then you also need to ask. So I mentioned that all the statements in this corollary are kind of easy translations of the tensor restriction theorem, but that's not quite true. The fourth item requires one additional ingredient, and let me explain that ingredient. That's one. So for the fourth item in the corollary, we use that finitely generated so-called fi modules over k are Noetherian. And so this is a theorem that goes back to Church, Ellenberg, and Farr, who were motivated by questions in algebraic topology, specifically the homology of configuration spaces of manifolds, which they realized have this structure as an fi module. And so let me say what an fi module is. This is just a functor from f from fi to z. And this fi is finite sets with injections. So this looks difficult the first time you see it, but it isn't really. Let me say what it means. So for every finite set, you have a vector space. And for every injection between finite sets, you get a linear map between the corresponding vector space. And in particular, if you take just one finite set and take a bijection into itself, then that gives you a bijection from this vector space to itself. So in other words, you get a representation of the corresponding symmetric group. So you can think of these functors as sequences of representations of the symmetric group, S1, S2, and so on, which also speak to each other in the sense that when you have a map from a smaller set into a bigger set, you also get a map from the smaller representation into the representation of the smaller Sn into the representation of the bigger. So, and finitely generated just says that you can find finitely many sets and vectors in the corresponding vector spaces here, such as if you apply all the linear maps that you get from here, you get everything. And material means that, well, either that they are that they satisfy the increasing the ascending chain property, or that it's generated by finitely many errors. So let me explain how that relates to this item 4. So in this item 4, what we have is a restriction closed tensor property X sitting inside our polynomial functor. Maybe V goes to P to the tensor V. Okay, and then we have this thing, the ideal of X, which lives in the coordinate ring of this functor, vanishing ideal of X. And now any one of the first 3 properties implies that this ideal of X is generated by polynomials of some bounded degree. So in Ix equals D for some B. So as I said, elements in here, when I evaluate that some vector space V, they are just functions from PV to K, but you can always realize them as polynomials, and then the minimal degree of a polynomial by which you can realize it is called the degree. And these are the polynomials in this ideal that have degree at most D. Okay, so by any of the first 3 properties, you can find that the ideal is generated by polynomials in some bounded degree. And this is sitting inside K of P at most D. So very concretely, in the case that P is V goes to V to the tensor D, then you should think of this as polynomials in the entries of your tensors of degree at most D. And you are allowed to mod out x to the q minus x. So that's what this thing is. Now this is easily seen to be, so now say S goes to K of P of K to the power S is, and then at most D. So you should think of this S as just the number of 1 up to n, but you can do it for any finite set. This is a finitely generated Fi module. Yeah, because, well, every such polynomial in the entries of your tensor of degree at most D is some linear combination of monomials, and in every monomial you see only finitely many in these. Essentially, that is why this is a finitely generated Fi module. And that means that this Fi submodule is finitely generated. So by Church Ellenberg. Ix at most D is generated by Ix at most be evaluated at k to the n0 for some n0. And this is the n0 that you need. Yeah, because this says that a tensor satisfies your property x if and only if every n0 times n0 times n0 tensor satisfies the equations that you get from this. So I think the time is up, and I'll stop there. Thanks.
Since
Sorry, I missed the last thing. What does this mean? The brackets k to the power n0, and what precedes it? The side of x sub b, and then there's the second set of brackets. How should I combine them?
Right. Okay, so let's unwind this. So maybe the functors are still here, right? So right, so Ix is a functor that assigns to B the vanishing ideal of x of B. Right? And so that you can evaluate at k to the n0, then you get all the equations for x of k to the n0. And then this just says you only look at the equations of degree at one.
you also, like you were saying earlier, you were also inspired by like the combinatorial, like what was it? This minor,
Yeah.
minors. Like, can you also apply some? This is really about vector spaces, of course, right?
Yeah.
Can you somehow apply it to combinatorial objects too? In a way, as a special case, or, or as a variation?
One of my favorite conjectures in this general area is that there is this thing called Santos-Grassmannian. People in physics, they study this because it parameterizes solutions to certain integrable systems, like the quantitative difference equation. Since you're at the quantitative institute, right?
Yeah,
So
that's right.
that seems appropriate to mention. And so this is something that dimensional Grassmannian, and as a topology, and it would be nice if that were an Euclidean with respect to the infinite symmetric group that acts on, because that would actually imply the graph.
Okay.
But I don't think that this theorem has any logical connection to the graph.
Yep.
Do you have a similar result of polynomial restrictions?
Yes, because polynomials are elements of also of the S to the D, right? And that's also a functor between S to the D, and that's that's also a polynomial. That's a special case.
And so you retrieve this result of Kashdan and Ziegler. Mid-rank.
Which result?
Well, yeah, that's a good point. So there's a result by Kashdan and Ziegler that says any restriction clause property of polynomials of a fixed degree D implies a bound on the Schmidt rank, or the strength or partition rank of, but in the case of polynomials. That's right. So we can get that not directly from the theorem, but from the proof of the theorem, in the same range where they get it, namely that the characteristic of the field is bigger than the degree. Otherwise, it's not match.
You happy? Yeah.